All right, if you're a developer who's ever worked with MongoDB, I bet you know that feeling. You know, the one where a query that should be instant just isn't. It takes seconds, maybe even minutes to run. Well, in this explainer, we're going to dive deep into how you can take those super frustrating slow queries and turn them into lightning fast operations. So let's get right into it. I mean, this has got to be the question that keeps us developers up at night, right? Why is my application so slow? Everything in your code looks perfect, the logic is totally sound, but the whole thing just feels sluggish. And of course, users are starting to complain, and you're just left scratching your head trying to figure out what's going on. Well, here's the thing. More often than not, that bottleneck, that performance killer, it's not actually in your application code. Nope. It's usually buried deep inside your database. So think of this as a bit of a detective mission. We're going to uncover exactly how your queries are performing, hunt down those hidden culprits, and fix them for good. Okay, first up, the high cost of slow, and how to identify the symptoms. Look, a slow query is way more than just a minor annoyance. It's a real problem. It frustrates your users, it drives up your infrastructure costs like crazy, and in a shared environment, it can even become this noisy neighbor that drags down performance for everybody else. So let's meet the main villain of our story, the collection scan, or call scan for short. What is it? It's basically when MongoDB has to read every single document in a collection just to find the ones that match your query. I mean, imagine someone tells you to find one sentence in a giant novel, but instead of letting you use the table of contents or the index, you have to read the entire book word for word from the very first page. That is exactly what a call scan is doing to your database. And it is, as you can imagine, incredibly inefficient. And this quote right here, it just cuts straight to the chase. MongoDB performance issues are 90% bad indexes. Explain plans never lie. The vast majority of performance problems you're going to face aren't some super complex, mysterious thing. Nope. It almost always comes down to bad indexes. And the proof? The explain plan. It never, ever lies. So that brings us to the next section, your diagnostic toolkit for finding a root cause. Okay, so how do we actually find these bad indexes, or even spot where we're missing one completely? Well, the good news is MongoDB Atlas gives you this awesome diagnostic toolkit to pinpoint the exact problem. So let's open it up and take a look. Think of Atlas as having your own personal DBA in a box, a database administrator. You've got the performance advisor, which suggests indexes for you. You've got the query profiler to visualize what's slow, and these are great for high-level insights. But for a really deep diagnosis, the one tool that every single developer absolutely must master is the .explain command. Yep, explain.execution stats is, without a doubt, your most powerful diagnostic tool. Seriously, using this is like getting an X-ray of your query. It doesn't just hand you the answer, it shows you the exact step-by-step plan that MongoDB used to get that answer. And in doing so, it reveals every single inefficiency along the way. It's amazing. So when you're looking at an explain plan, think of these 3 metrics as the vital signs of your query's health. First up, the stage. What you want to see here is IX scan. That's your confirmation that an index was actually used. Next, total docs examined. Ideally, this number should be equal to, or at least very, very close to, n returned, the number of documents it gives you back. And finally, execution time millis. Your goal here? Keep it under 100 milliseconds. And just look at this comparison. I mean, the difference is literally night and day. Before the index, you've got a call scan struggling through 5 million documents. It takes over a second. But after adding just one correct index, bam, we get an IX scan. It only has to look at the 50 documents it actually needs, and it comes back in 10 milliseconds. That's 120 times improvement from one single change. It's incredible. So now we get to the ESR golden rule, which is really the core treatment for slow queries. We know we need indexes, that part's clear, but how do we build the right one? Especially when our query is filtering on multiple fields. Well, the answer is what I think is the single most important concept in all of MongoDB indexing, the ESR golden rule. Okay, so when you're creating what's called a compound index, that's an index with more than one field, the order of those fields is everything. I can't stress that enough. For the index to work properly, you have to follow this exact order. First, you put the fields that you're using for an equality match. Next, you put the field you're using for sorting. And finally, last, come any fields used in a range query.
with greater than or less than. So equalities sort range. That's the ESR rule. Get that order right. All right, let's put this into practice with a real-world e-commerce example. Let's say our query is looking for a specific customer ID and a status of pending. Those are our equality filters. Then it sorts the results by order date. The optimal ESR-compliant index follows that order precisely. Customer ID, then status, then order date. And it is blazing fast. But look at the suboptimal one. If we mess up the order and put order date first, MongoDB can't use that index to help with the sort anymore, and performance just craters. The order is absolutely non-negotiable.
Now, let's talk about writing smarter queries, basically preventative care and best practices. Because, fixing slow queries is great, but preventing them from ever happening in the first place, that's even better. So let's go over a few best practices for writing high-performance queries right from the get-go.
This one sounds simple, but it is so powerful. Always use projections to return only the fields you actually need. Don't ask the database for a whole giant document if all you really care about are 2 or 3 fields inside it. By using a projection, you tell the database exactly what data to send back. This cuts down on network traffic and memory usage on both your application server and the database server. It's a huge win. And that idea leads us to what many people call the holy grail of query optimization, the covered query. This is the special, hyper-efficient state where MongoDB can answer your entire query just by looking at the index. It never even has to go and read the full documents from the desk. The answer is right there in the index, which is already in RAM. As you can guess, this gives you a massive performance boost. And you know what? Achieving a covered query is actually simpler than you might think. There are just 2 rules you have to follow. First, all the fields you're filtering on have to be part of the index. And second, all the fields you're asking for in your projection must also be part of that same index. That's it. You meet both of those conditions and you've just unlocked this incredible performance gain. Okay, a quick tip for anyone using aggregation pipelines. The number 1 most important rule is filter first. Always put your $match stage as early as you possibly can in the pipeline, preferably first. Why? Because this makes sure that all the later, more expensive stages are working with the smallest possible set of documents. It makes a huge difference. All right, moving on to some advanced indexing strategies. These are kind of like specialized tools for special cases. The ESR rule we talked about, it's going to cover most of what you need. But sometimes you run into specific problems, and MongoDB has some very clever, specialized indexes to handle them. Let's look at a couple of powerful examples. So here are 2 really useful ones. First, you've got partial indexes. These are brilliant when you know you're only ever going to search for a small subset of your data, like documents with the status of active. You can build an index that only includes those documents, which keeps the index way smaller and faster. Then, on the other side, you have TTL, or time-to-live indexes. These are perfect for data that expires, like user sessions or temporary log files. You just set a time, and the index will automatically delete the old documents for you, keeping your collections nice and lean. Okay, let's wrap this all up into a super practical, real-world optimization checklist that you can go use on your application, like right now. First, are my queries using indexes? Check for that IX scan. Next, are my compound indexes ordered correctly with the ESR rule? Am I projecting only the fields I actually need? And this is a big one. Are there any unused indexes slowing down my writes? Remember, unused indexes aren't free. They take up space and they slow down every write operation. So make sure you audit them and get rid of the ones you don't need. And finally, is my $match stage at the very beginning of my aggregations? And that really brings us to our final thought here. You have to remember that your queries and your data, they change over time. Optimization is not a set it and forget it kind of task. As your application evolves, new query patterns are going to show up and old ones might disappear. So performance tuning is a continuous process, a habit. Which leads me to this final question for you. When was the last time you really audited your indexes?